Hello, this is a presentation on wine quality prediction. This is applied to machine learning. It's just an overview on how you can perform a machine learning project from front to end and what everything entails regarding that. So the purpose of this project using the data set is to predict the quality of wine. There's a number of columns. In stats, you might call those variables. In machine learning, you call them everything from attributes to features to columns or vectors or etc. And those include acidity, chlorides, pH, alcohol, etc. At the end of the day, we have 11 of these feature columns, and then we have one predictor column, which is wine quality. It's supposedly on a scale of 1 to 10, although when we actually get into it, we won't see that's the full range of values. And given that it's 1 to 10, we could bin these and aggregate the data accordingly. So what we're going to do is we're going to find the best model, and then we're going to optimize that model and go forward. The software used in this let's say Spider, Jupyter, and also Matlab. For Python, it's a nice versatile tool. It does everything from extract zips to read from websites, as we'll see. It's pretty versatile and has a large scope, whereas Matlab is a more specialized tool. It replaces Maple, which was maybe, I don't know, in 2001-ish. I think they got bought out or shut down. It's an excellent program. The total lines of code in this was over 900 lines to produce everything in this presentation. So we'll go over several segments. The first segment will cover importing to pre-process, exploration, splitting the data, and clustering the data to look for some patterns, patterns. The second part will train and then score the training models. We're going to regularize and train those regularized models, optimize and score the optimized model, and then finally look at voting and model of models. Regarding the data set, it came directly from the University of California Irvine Machine Learning Repository website. It's a great resource. Let me just pull that up. I think that's an art anteater, not an aardvark. Yeah, so this website here, UCI, they've got a lot of different data sets. If we go to view all data sets, do they give us a number? 440 data sets. For this presentation, I'm using the wine quality data set. There's several wine data sets out there. This one explores both red and white wine. We can go check out the data right here. I'll pause. Well, it's been several minutes and it's not done loading, so we'll just move on. Neither of these links work, so there we go. Oh, there it is. So here we go. We have a red wine data set and a white wine data set along with the names and some of the descriptions as to what these are. See, they're calling them variables here. So this data set did not require any cleaning. The red data set was much smaller in terms of row count, or n, than the white column, or the white data set. There were no null entries. If there were, you'd have to adjust your models accordingly. Here's just a preview of what that Python code would have looked like if we dug into that. The predictors are all numerical, and later on I standardize them after doing the train test split. You want to make sure that you do that. Standardize after you do the split, not before. And so then the actual categorical features, they're ranged from 3 to 9. So let's take a look at that. Here we can bin or aggregate the labels or the y values accordingly. Or I'm sorry, I'm saying accordingly a bit much there. So we have wine bins. I'm binning it by 2, I'm binning it by 3, 4, and then 7, which is the default. And looking first at the default, we see that there's a couple of 3s, there's a few more 4s, but the vast majority are 5, categorized as 5 and 6 qualities. A couple 6, 7, 8s right there, can't read that. So this is important because, you know, to describe the data set, first we want to say that this is the best and this is the worst of the wines. And we do see immediately is that there's quite a bit of skew. So our mean might be there, our mode is there, but our median is going to be on the right hand side of that distribution, not on the left hand side. So we can bin the data however we want. I tried to bin it, we're going to ignore the skew in this. I tried to bin this between we're going to say from 0 to up to 6 is how this bin works, and then above 7 and up to 10. So this is between 6 and 10, and here we have 0 and 6. Here we get kind of an even distribution, and what we see is, okay, so that's enough detail on the bins. We go through various bins. Check the correlations. On the white wine, interesting, and the red wine, we see different correlations, and so we see a strong, we can ignore, let's say, the top halves of these charts. They're just a reflection of the lower half. So we see strong negative correlations, positive correlations, and a slightly strong positive correlation there. But if we translate from over here and explore here, we don't see those same correlations. So it's just kind of an interesting observation. We see stronger correlations elsewhere. So what that means is that these features don't carry the same correlations from white wine to red wine. And here's just a graphed version of that matrix. And so the correlation matrix. We can see a strong correlation here between density and residual sugars, and so apparently as sugar, or let's say as sugar content goes higher, then the density of the wine increases. And I think I saw an interesting negative correlation between alcohol content and, let's see, density. Where is density here? Right there. So in this relationship, we see that as alcohol content increases, density decreases, which makes some sense since sugar is a solid and alcohol is a low dense liquid that can change states. So we have in Python, let's just jump over, I think I have it open. Yeah, here it is. So this is with the IDE Spider. I did not use the alternative and common one called Jupyter. Jupyter is nice for presentations. I like Spider because it's just a classic IDE, and you know, as previously mentioned, here we have the CSV being read directly from the website, defining the header, defining what the separation values are, etc. So we jump through. Everything gets binned. We export it to a location on the hard drive, the temp drive, and I'm just using variables here, variable names. At the start, I define those variables, and what I'm doing here is I'm just saying, okay, now we're going to work with 4 bins. We're going to change the 4 bins to that, and then we run the code, and everything works for us. And exports to an appropriately named file name. So that would be exported as white 4. So I use the Python code train test split. I'm doing a bring that pointer back. I'm doing a 70-30 split, which is reflected by this test size equal to 0.3. Random state is 1, 2, 3. Immediately look at clusters to see if there's anything natural that we can work off of. So we bin it by 2. Sorry, when we look at 2 clusters here versus 4 clusters versus 7 clusters, we see some strong internal coherence right around here. And that internal coherence drops down quite low. And the in terms of the separation, we also want we want high coherence, high separation. What that means is that we might have a cluster right here, another cluster right here. Well, this cluster has strong internal coherence because the distance between each of these points is quite small, so they're dense, they're grouped together, and then these points to those points, those are quite far, so there's good separation too. So separation right there, coherence, internal. And if we had some highly scattered clusters like this, and a second cluster right here, and imagine these are blue dots, well, here's one cluster, here's another cluster. Look at that lack of separation and lack of internal coherence. What you can do is you can erase some of these points here in order to increase the separation, and these points would be represented by these middle grounds right there. Oh, and so, you know, do we find any great clusters? Nah, nothing too convincing. So now we're going to train and score. So using the Matlab tool, which is, let's just give you a preview of that right here. Just for learning sake, if you use a double parenthesis, it's creating a section. If you hit Control Enter, it'll run that section. Put the cursor down here, run it, or put the cursor here, Control Shift Enter, run it, and jump to the next code section. And so it makes it quite nice to run through it all quite quickly. And over here in the workspace, we can see our variables, and we can explore them by double clicking and taking a look at them. And we can even, I think, sort them. Yeah. Great. So here are all the models that were tested. I'll explain what these are. We have 2 bins in this top left corner. 2 bins. Okay, yeah, right. So this is red up here. This is white. So we have 2 bins. You know, I just did a elementary examination of the red. I drop it later on. It's just for curiosity's sake. So we're really talking 2 bins, PCA turns on, off, PCA turns on, PCA turns on, principal component analysis. It's a dimensionality reduction feature which keeps all the information within. We have cross-validation, which is a much nicer alternative to the train test. If it's in the function, use it. If it's not, too bad. The thetas here are the columns, and so we have y hat equals x1 theta 1 plus x2 theta 2 plus x3 dot 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 xn theta n, and each of these thetas are weights. Each of these x's are the let me just jump back to Matlab and show you. We go to all features here. These are the x's: alcohol, chlorides, citric acid density. Those are the x's, and we multiply each of those x's by a weight or a theta here. And so we're forming those equations, and we're optimizing the weights in order to get the most accurate y hat fit, or the prediction y. So what do we see? We see that when we go through the different bins with the different PCAs on off, different CVs, we get I'm gonna circle in the bottom left, for instance, right here, the ensemble. That's an ensemble bagged tree. You probably can't read that due to compression of this video. Again, the ensemble bagged tree. Up here, the ensemble bagged tree. These are always the most accurate model at 83% here, 83%, 68%. And the 4 bins, notably, the accuracy drops to the lowest at 70%. When we look at those ensemble bag trees, they seem to be our most accurate predictors. Let's see, what I'm doing here is I'm testing various ensemble models. So we have bagged trees, boosted trees, bagged trees, which I stopped because I realized that I just did that one, and others. And so here we're exploring the ROC curve, the receiver optimizer. It's the receiver optimizing characteristic curve. I can't quite recall, but interestingly enough, it was developed in World War II while they were using radar to try to distinguish between bombers and clouds. And so this was a technique that was recently developed. Here's my pointer. So the area of the higher the area under curve, the better. We want to maximize that and bring it as close to 1 as possible. So if it was equal to 1, we would have everything being labeled as a true positive and nothing as a false positive. So it would be making all guesses correct. What it displays, how to interpret this graph, is it shows you how soon the model starts making mistakes. And so, for instance, this one starts making mistakes sooner than this one, which is actually really quite strong. Whoa, that's this one right here, actually, the big one. We have confusion matrices here for the different setups that we've gone through, these different models here. Our favorite is the ensemble bag tree, where we see, okay, so the predicted class is 0 so let's talk about this and this right here, 73. We're predicting that it's a 0, and lo and behold, it is a 0. Let's talk about this. We're predicting that it's a 1, and lo and behold, it is a 1. However, up here, we're predicting it's a 1, but it's actually a 0. So it's a false positive rate of 27%. So that's good. That's great. You want to see high numbers here, and lower numbers in the opposite diagonal. So after examining 270 pre-regularized models, we see that using the various binning methods of 4, 2, 4, and 7, the SVM support vector machine is outperformed by KNN, which is outperformed by ensemble. And that's a generalization. If we go back to these, you're not going to be able to read this because of compression again, but the ensemble, most accurate ensemble, is more accurate than the KNN, which must be around here, and the KNNs are more accurate. The most accurate KNN is more accurate than the most accurate SVM. So comparing the best to the best, or the best, it's ensemble over KNN over SVM. So now that we've explored the unregularized models, we're going to check out what regularization does. Using Lasso Regularization, just as a note, let me look up how to use different colors. Okay, so there's not a way to change the ink color using a shortcut, so I'll do it here. So I was going to show the regularization. So let me erase that and restart, and I think I can hit W. Yeah, cool. So W to bring up a new white sheet. I'm just gonna pause while I draw. Okay, so before I start drawing everything on here, I'm just gonna do a quick exploration of regularization. We start with a mean square error. If this is a linear regression, it's the measure of fit. So the error term, well, I guess I'll do that right here. So we're going to place some dots on the slide here, and these are dots. And if we're going to fit a line to this to these points, let's say it's just like from high school, we see y equals mx plus b, where m is equal to the slope, b is equal to the y-intercept, so b might be equal to 0.2 here. And x are just the values here on the x-axis and y on the y-axis. And so we draw this curve and we measure how much how accurate or how much this curve tells about the points. What we see is that the points are sometimes close to the curve, right here, here, and here, but sometimes the points are far away from the curve, here, here, and here. These points that are far away might be called outliers. And our purpose, if we add up all these vertical lines, this line right here, this line right here, this line right here, this little line, and this long line, well, by the end, after we've summed those up, oh, that's a really bad sum mark, but we want to minimize that. So our purpose is to minimize the error that we see here. Imagine if our line were, I'm going to use a color other than green, purple. If this was our line, well, then our error associated with that line would be very high because it would be very far away from all the points. So we'd see this point would be close, this point would be close, but what about this point? We're going to get a lot of error from that one point. And so the best fit line is right there, and we want to minimize the distance between those points. And of note, this is just one of the features. We're working with 11 features, and so it's an 11 dimensional space, and so we can't really draw that on paper. So the regularization is seeking to let me get rid of this here. Oh, hold on. We have a complexity measure right here. We have regularization. We have minimum mean square error right there. There's an inverse relationship between C and lambda here. C is complexity, lambda is regularization, and so if you were to increase lambda, then all things being equal, the C would have to go down. And on top of that, if we set regularization to infinity, then complexity would drop to 0. Now let me use a different color here. We're going to explain what complexity is. I'll just use that. So C equal, I'm going to pause. So our complexity function is the absolute value of theta 1, theta 2, and theta 3. We want to make sure that these theta values are standardized. And so we've already standardized the x's in the previous chart, in the previous table in Matlab. And again, if theta ends up going to 0, then due to the inverse relationship, regularization will increase to infinity. And what does that mean? So if I'm still here. So if lambda increases to infinity, then these weights will drop to 0, what does that mean? It means that we're going to be multiplying the, remember, oh, that sucks. Okay, so let me just find something else. Okay, so these are our standardized x values. If regularization increases to infinity, then we'll multiply this value, this value, this value, this value, this value. All of these values will be multiplied by 0. Our thetas are our weights, and so when we multiply this column by 0, you know, everything reduces to 0. Everything reduces to 0, leaving us with the mean square error. And now we go back here and we can kind of visualize that. So here we're applying the regularization. Here regularization is equal to 0. Here it's equal to 1 actually. So as we go to the left, the regularization is increasing to 1. So in other words, its impact is the strongest over here. Now we're on the laser pointer. So as regularization increases, we can actually determine between these two lines. Here's a 1 standard deviation between the two lines. We're going to want to choose a regularization value somewhere in between here. And if I can zoom in, great. Oh, you can't use a laser pointer when you're zoomed out. Control P? Nope. Okay. So as we increase regularization, right here we're going to choose this point, and at this point we've seen that some of these coefficients, these thetas, have hit 0 due to the regularization factor, which means that some of those x columns, when multiplied, equals 0. So our equation thus simplifies. So we're able to achieve a certain level of accuracy given a certain level of simplicity in the model. This model is more robust because it's working to explain less of the noise, less of the random variability in observations, and it's just saying, approximately this is what we're going to see. The benefit of that is that we're not overtraining the model. It's not a model that's just memorizing every movement in the different features and explaining 100% of their movement. Rather, it's saying, this is what we think is happening. It's a simple picture, and when you move that simple picture from the training set to the test set, well, then it's going to perform better because, again, it's not memorized everything that happens in the training set and applying it to the real world. There's some room for ambiguity in the model. So when we look at the different bins, we see that the 2 bin, the 4 bin, and the 7 bin, actually we see the coefficients drop to 0 at different rates. For instance, here we see total sulfur dioxide and sulfates never even make it into the regularized model here of the 4 bin or the 7 bin. Furthermore, they drop out at different rates depending on the binning. Volatility, acidity, and free sulfur dioxide switch positions between the 4 bin and the 7 bin, and this reveals the non-static nature of model building, or the ability of these models to really change on the slightest tuning of your models. And so you have to be very aware when you're describing these models or exploring these models how prone to change they are. And so if we're going to try to make a broad generalized statement about wine quality and its relationship to volatile acidity, we might say, if we'd broken this into good and bad wine data, good and bad classification, that volatile acidity is the leading predictor, as well as for the 4 bin it would be true, but if we jump to the 7 bin, well, then it's not any longer. So statistics can lie. We re-examine the clustering using k-means, using k equal 2, k equal 4, k equals 7, and we so it's still not very interesting. After regularizing, we once again run it through all the previous models. I'm not running it through support vector machines, canceling those out because they just take too long to process, especially I think it was the cubic and the quadratic. Yeah, and of note, you have fewer n or observations. Support vector machine is going to do a bit better, but as the n number increases, it's going to take a long time to process, a very long time. So after looking at 170 post-regularized models, we see the same relationship. Ensemble, the best ensembles outperform the best KNN, which outperform the best SVM. Bag tree ensembles were the most accurate. So we're going to focus on 2 bins going forward, just because you have to be realistic about time management. So we did see that regularization slightly decreased the accuracy, as expected. So now we're on the second to the last step, which is optimizing the model. Ignore that text right there. This is a visual representation of the ensemble bag tree. The default number of trees in the best performing model was 30. We used the bagged approach, and the Matlab model was called fit ensemble. And I'll just jump to the Matlab code to let you see what those look like. Here it is. So where's my, okay. Here's my fit ensemble with actually, okay, so I used 10 in this model right here, but I'm doing something else. And we might see another model right here, the fit KNN. We're setting it equal to 10. We're doing SVM fine Gaussian here. So that's Matlab for you. And the total runtime on that model was 16 seconds. So now that we've found the best model, we're going to optimize it using the hyperparameters. We're not going to call them parameters, because the parameters again are y equals x1 theta 1 plus dot 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 xn theta n. These guys are called parameters, so we can't use that word again. The hyperparameters are the meta parameters, you might call them. So what that means is, can I find it here? Number of trees is a hyperparameter. Number of splits is a hyperparameter. Pruning of the tree is a hyperparameter. So our base model is at 67% accuracy with 30 trees. As we increase the trees from 1 to 500, understandably, we should see accuracy increase. However, this is due to a more complex model, which means that when we take that model out of the training data set and have it perform in the real world, it's probably going to underperform a more simplified model. And what that means is, let me pause to draw. So here we have our we have our test right there, and we have our training right there. The accuracy of the training model is, well, let's say the error of the training model is going to decrease as we build more observations. Now when we take it to the real world, we're going to see that at some point the test is going to have low error, great. This would be the optimal level of complexity here, or regularization, whatever. But if we keep going with the data set, then the test set, then the error is going to start increasing over the training model. At this point we would say that it is overfit. At this point we would say that it is underfit, because the test is not describing is not able to describe enough of the error away. So as we approach down here, this would relate to this side of the graph, and up here this would relate to this side of the graph, and somewhere in between we should see the best fit model. I did not regularize this model. Moved on. So this is an example of the 7 bin. Can't find my cursor. So 1, 2, 3, 4, 5, 6, 7. We see that jaggedness. That's due to the fact that there's not enough observations around here. On these peripherals, we don't have enough observations, and so there's not enough data points to build a smooth curve. It's a bad sign. A resulting confusion matrix. So now we're just going to do the voting, the final step. We're going to explore hard, soft voting, and then model of models. So the two voting methods are different. They're going to result in different results, and we're going to use, for the hard voting, the classes and probability scores for the soft voting. And so when we fit a model, we're given as output both class and score, and each of these is a vector. And for class, it's either, for this good or bad, it's either going to be 1 or 0, and score here is actually probability, which is going to be between 0 and 1. That should be brackets. We explore the 4 models: ensemble, weighted KNN, SVM, and complex decision tree. And here's for our hard voting. What we do is we just find the mode of each row. In other words, we say majority wins. And so here the result, because there's only one number 1, the majority rule would say that's a 1. Here the majority would say that's a 1. That should be a 0. Sorry, I misspoke. Simple enough. Now, of note, I have an even number of columns here. So when it's a score, I'm not exactly sure. I didn't look into the data set to see what would happen, but I think that what you want to do is make sure that your columns, or your thetas at this point, or your, okay, getting too early, your models that compose the voting are going to be odd. Soft voting is whichever model screams the loudest gets the vote. Here I have the 3 models, but I have 6 predictors, and so this is actually model 1 predicting class 0. This is model 1 predicting class 1, model 2, etc., etc. So you see that these two columns add up to 1. So they're same coin, 2 different sides of it. For that reason, I just want to eliminate one of these columns, one of these classes, from each score vector, or score table, matrix. And I do that with the following code. At the end of the day, we get the max for each column, for each row. So in this row, that's the max for each. I'm sorry, this is the max, 1, 1. Over here, we're going to see 0.85, 0.96, and I'm just working out the evens. Okay. So between the performance of the hard and the soft, we see 61 total differences in the vote, or 4.1% different, and the soft voting predicted more good wines than the hard voting did. We have our confusion matrix. with accuracy. Of note, accuracy you don't want to run off of entirely. I did it earlier because we were working with 400 models. You actually want to kind of compare these numbers as well, and each one of these numbers will consider these various factors in relationship to each other. So the model of models, here what I'm doing is I'm taking, do I have it? I'm taking these three models, the complex, the bagged ensemble, the weighted K&N. I'm taking each of these models, and y equals x1 theta 1 plus x2 theta 2 plus x3 theta 3. Here each of these x's is the score, probability score, of one of these models. So this is interesting. So we're taking those x's and giving them weights. Multiplying them together to get our y prediction. And so we're building a model of these models. So the prediction turns into our inputs, and we associate with each of those inputs a weight, and that gives us our y prediction. Here the model that I'm going to do is a lasso, and as a result we see which model has the largest impact, that's the absolute value impact, on the y result. And here we see it's the K&N and the bagged ensemble are the strongest predictors, whereas the complex DT just drops out. And went back, fixed this, fixed this, fixed this. So really the wish list, I didn't do the minimum spending tree. The minimum spending tree is, let's say, the distance. This is regarding to the clusters. And this is observation number. You can see when you have a cluster diagram, you can see that the distance from point 1 to point 2, 3, 4, 5, 6, the distance between these points are quite small. And we jump to the next one, big distance, big distance, big distance. These distances, these big distances are marked there, and they kind of indicate how many clusters you have. So this might be one cluster, 2 cluster, 3, 4 clusters. So it'd be nice to have produced that graph just for another visual of the number of clusters we might expect. I didn't do the train test error graph. As said, I only used accuracy. Microsoft Azure has something called the parameter sweep, where you test all parameters. You saw earlier where I had tested the ensemble with parameter of number of trees equal 5, 10, 50, 100, 500. Well, the parameter sweep would go from 1 to 500 continuously, well, using integers, and found that truly the best model there. I didn't regularize the bag tree ensemble. I would have preferred using a odd number of trees, or of models to vote with, as well as building more models. I was running short on time. And as well, I never went back and checked the red data set. So there you go. Thank you for watching.